Good evening. My name is Thomas Richardson. I'm a sophomore student at Mass Maritime, and today I'll be presenting on how we use calculus, specifically derivatives, to find the maximum height of a ball. To kind of zoom out and broaden the scope of this presentation, we're going to show how derivatives can help solve real-world problems. I know, at least for me, it's very helpful. Math is not a strong suit of mine to apply. This is an applied calculus class, so to apply these skills that we're learning to real-world applications. So here we have a function, h of t is equal to negative 16t squared plus 64t plus 5. H is equal to height, and t is equal to time, and so this function, h of t, is equal to height of the ball after this time. So this function shows us that the ball will be thrown, it's going to rise, it's going to reach a high point, and then it will fall back down. So in order to solve this problem, we need to take the derivative. The derivative represents velocity, and the definition of velocity is the rate of speed which an object changes its position. So when velocity is set equal to 0, that's when the ball is at the peak or its highest point before it begins to when it's rising and when it's falling. That's when it's at the highest point. So in order to solve, we need to set this derivative equal to 0. So to do that, we subtract. Once we set it equal to 0, we just follow our basic principles of algebra. Negative 32t plus 64 is equal to 0. So we subtract 64, so it's negative 32t is equal to negative 64. Divide by the negative 32, and we get 2 on the right-hand side, and we get t. So time in seconds is equal to 2. So now we need to use that information, the time, seconds is equal to 2, back into our original function, the original equation. So h of t is now h of 2, t is equal to 2. So similar to that, setting that derivative equal to 0, we plug the 2 in, and we just do our standard order of algebraic operations. 2 squared is 4 times 16. We get plus 64 times 2 plus 5. And the height, h of 2, is equal to 69. 69 feet is our height. If we plug this function into a graph, it looks a little bit like this. So on our y-axis, we have height, or h, in feet. And on our x-axis, we have time, which is t from our original equation, and that's in seconds. So if we follow the left-hand side of this graph, if we're at the x-intercept here at 0, the x-intercept at negative 0.08, we realize, so this, to kind of visualize this concept, that's when the ball is thrown. And as it goes up and up and up, that's when it's rising and rising and rising. And once we hit right up top here at 69 feet, if we travel over on the x-axis, we get 2 seconds. So to throw that into context, that's when you throw the ball straight up. After 1 second, 2 seconds, the ball hits 69 feet above you, and then it's going to fall. So on the right-hand side of the graph, as we're slowly losing velocity or height, as we're going down in height, the seconds go on. So by the time we hit 4.08 seconds, that's when the ball hit the ground again. This concludes my presentation, and I hope this provided you a little context on some real-world applications of calculus, specifically derivatives, like I mentioned. I appreciate you listening. Thank you.